Good morning, everyone. Thank you for joining us for the eighth and final joint education session between AMCA and Odell Associates. Today's topic is stall detection and control in commercial and industrial fans. And for those of you who surprisingly would not know who I am by now, I am Lisa Cherney, the Education Manager for AMCA International, and I'll be moderating today's program with our speaker. Some brief notes before we get going. The audience is muted during the program. If you do have questions you would like to submit, you can do so at any time from the AirMeet platform, and we will address those in the live Q&A at the conclusion. The session is being recorded. The recording and the PDF version of today's slides will be posted on the Odell website within 48 hours. And if anyone wants to earn PDH credit for today's program, we do remind you that you need to stay on for the entire hour, and then please complete the survey that will be emailed to you after the conclusion of today's program. And for anyone who is not seeking credit, we still do request if you complete the survey. We appreciate any feedback you'd like to share. Again, for Q&A, please go to the interactive panel on your screen. Click the Q&A option at the top, type in your question, and click send. And a reminder that all chat messages and all questions submitted on screen in those panels can be viewed by the entire audience and the speaker. And if you do have a question for Jeff Sheard that's a little too involved to type out, please go ahead and use the raise hand icon at the bottom of your screen, and we can unmute you to verbally ask that. PDH credits for the program are being issued through RCEP. AMCA has met the standards and requirements of RCEP to issue those credits, and everyone who qualifies will receive an email within 30 days with a summary of credits earned and a link to a printable certificate. A quick disclaimer that today's program is provided as an educational service only. It is not intended to serve as professional engineering and/or manufacturing advice, and the views and opinions expressed are those of the speaker and do not necessarily represent the views of AMCA International. In making today's activity available, AMCA is not endorsing, sponsoring, or recommending a particular company, product, or application, and note that under no circumstances, including negligence, shall AMCA International be liable for any damages arising out of a party's reliance upon or use of the content. The program today is copyrighted by AMCA International, and I'd like to introduce to you our speaker for this session. Dr. Jeff Sheard is president of AGS Consulting, LLC. Jeff has over 40 years of experience in the aerodynamic and mechanical design of rotating equipment. He is recognized as an international expert in fan technology and development of high efficiency fans for commercial and industrial applications. Jeff holds a Bachelor of Engineering in Mechanical Engineering, a Doctor of Philosophy in Aerodynamics, and a Doctor of Science awarded for the application of aerospace design techniques in commercial and industrial fan design. Jeff is very active in AMCA International and has also been the chairman of the FAN 2012, 15, 18, and upcoming 2022 conference organizing committees. He's a very busy and very knowledgeable presenter for today's program, and we are lucky to have him joining us. So, with that, I will stop sharing my screen and turn it over to you, Jeff.
Thank you very much for the introduction, Lisa. Let me share screen. Do you see my screen? Okay. Can you see that, Lisa?
Perfect.
Excellent. Okay, well, today we'll run through what aerodynamic stall is and why it's more important in some fans than others, particularly axial fans, and also look at a few strategies for selecting fans such that stall can be avoided. If we have time, we'll spend a few minutes discussing how one might monitor the fan to ensure that it doesn't go into stall. So we have an agenda in parts here. We'll start, as I said, with a discussion of just what stall is. We'll keep that fairly short. I'm using pressure pulses as an example of how fans can end up in stall. It's not to say that this is the only way fans can end up operating in stall. It's just an example. I need to use something to illustrate the issues, and I just happen to pick on pressure pulses, but it's relevant to any application issue that will result in a fan running in stall. I'll then present three strategies for keeping a fan safe in the event that stall is a possibility. Anti-stall casing treatments have been popular in the past and are still sold today, so I'll mention those. Spend a little time on mechanical failure mechanisms and safety factors. We don't really have time to get into the detail of fracture mechanics and fatigue failures, but we should at least mention them. Then I have a few examples and the cost implications, and then finish with some conclusions and supplementary material. So,
And Jeff, if I could ask you to please hide the banner at the bottom of your screen.
oh, very good.
Thank
There
you.
we go. Yep. So, what is aerodynamic stall? Here we've got a graph showing flow on the horizontal axis versus pressure on the vertical axis. If we go to this point at around 13 meters cubed per second at 0 pascals, this is a fan characteristic where the fan characteristic moves to lower flow as pressure increases. We've then classically got a system resistance, which is this hockey stick curve. Where the two actually cross is where the fan operates. And we can see we've got a degree of curve left before this sudden drop. And this sudden drop is stall. It's the practical consequences. So we see the pressure falls with decreasing flow and then recovers somewhat. But what's happening there in practice is that before stall, the flow is going through the blading as intended. As we get to stall, the pressure across the fan, the outlet pressure is higher than the inlet, it just becomes too great for the blading and the flow starts to break away. That manifests itself as turbulence, buffeting, the fan's simply not operating as intended. And there are a variety of negative consequences associated with that. So it's helpful just to think in terms of different types of fans when considering the significance of stall. If we look at a centrifugal fan over here on the right, number B, the flow comes in axially and out radially. Cross flow fan, in radially, out radially. Mixed flow fan, in axially, out at least partially radially. So an axial fan is unique in that the flow comes in axially and goes out axially. And that's significant because as you approach stall, the flow through the blading slows down. The axial fan impeller is still rotating, so it's thrown out under the action of centrifugal force. So if you have a centrifugal, cross flow or mixed flow fan, the fact that it's thrown out radially by the simple fact the impeller is rotating is a mitigating factor. In an axial fan, the flow is not supposed to go radially, it's supposed to go axially, and if it does go radially, it ends up on the casing. The outlet pressure is higher than the inlet pressure, so the flow ends up getting driven out of the inlet, which is not what anyone wants. So that results in the axial fan having a more severe stall than any other type of fan. So it's not to say other fans don't suffer the effects of stall, but it's not generally as severe. And we can see that in this next slide, because if we just pick, this is a collection of fans which have got some comparability described here, A through G, and we can see this is your highest pressure centrifugal. It's a steeply rising characteristic, and it only falls very close to shut off. You'd never actually operate a fan here unless you accidentally closed a damper. But if we look at this typical axial fan here, we're rising and we're falling really quite far from a zero flow. There's a lot of opportunity to operate the fan accidentally in this region. So axial fans have characteristics which allow accidental operation in stall more freely than a narrow centrifugal fan. So the consequences of operating an axial fan in stall are more severe, and the probability of accidentally doing so is higher. So that's why we'll really focus on axial fans in today's presentation. So pressure pulses. As I say, I'll speak about them not because you're necessarily particularly interested in them. They may not apply to the applications you work in, but it's just a way that a fan can accidentally end up in stall, and it's equally relevant to the methods for selection strategies for managing stall. So when we exceed the maximum pressure developing capability of a fan, it does stall, and that can happen transiently. That will still lead to a failure. So in a tunnel, a metro system, you have tunnels with trains running in them. Typically you have a positive pressure pulse. There's a piston effect as the train goes down the tunnel. So a positive pressure pulse of maybe 300 pascals in front of the train and 300 behind. One thing that became popular in initially Asia, but also Europe, was the use of platform screen doors. There were some extremely unfortunate accidents where in very crowded stations, people got literally pushed off the platform accidentally in front of trains as they were coming into the station, with a predictable consequence. So these platform screen doors became popular. They remain shut until the train is in the station and the doors are open. An unintended consequence of this was that the air in front of the train used to be able to, up to a point, disperse in the stations. As soon as you put a series of platform screen doors, you now trap the air in the tunnel. So the pressure pulse is more than doubled from 300 to 600 or 700 pascals, following which we had a spate of in-service central tunnel fan failures for no apparent reason. So this led on to a keen interest in selection strategies for avoiding stall, and I'll run through those now. So if you know what might happen at the time you design the system, then you're in a good position to select a fan appropriately. But pressure pulses are quite difficult to estimate. You don't know if somebody's going to put platform screen doors in 10 years' time, or if a new generation of trains is going to be going faster. And similarly, in any other application, you have similar uncertainties in any system that's going to be lasting for 10, 20, 30 years. So We then have another variable in that just because you operate in a fan install, you don't know how long it's going to necessarily take to stall. That's a function of its mechanical design. So it will fail, but not necessarily particularly quickly. So there's a variety of uncertainties associated with the operation. And we have three basic strategies when it comes to selecting a fan. One of the idiosyncrasies of axial fans is at low blade angles, they don't stall. If they're lightly enough loaded aerodynamically, they don't stall. We can simply select a fan conservatively that can generate far more pressure than we think we need. And there are anti-stall casing treatments, which I'll come to in detail later, which can essentially provide some prevention in the effect that one does stall a fan. So non-stalling blade angles up to about 16, 18 degrees blade angle on an axial fan, the characteristic simply rises continuously back to zero flow. It doesn't stall. It's not heavily enough loaded to stall. The problem with it is you can see we're right down at about 2 meters cubed, and we may want to be operating at more like 12. So you're going to need a significantly bigger fan to get up to the sort of flow rates you expect. But nevertheless, if you're willing to spring for that, it's going to be a low risk option. If this is our nominal fan curve and these two upper and lower green lines are our pressure pulse, you can simply select with plenty of pressure developing capability above. It's a fair strategy as long as you can predict what's going to happen in the next 30 years. I always feel anyone who thinks they can predict what they're going to be doing more than a year in advance is being very optimistic. But it is nevertheless a strategy that's popular, primarily because it's cheap. We'll come to that later. Then we've got these anti-stall casings, which are something which I'll explain in a little more detail. They're not particularly intuitive, but they work remarkably well. So if we move on to the anti-stall casing treatment, well, it's quite an old technology. It's been around for a while. The first generation, this is a cut and paste from the initial patent. We have a rotor here, and there's actually a slit in the casing here, an annular slit, and then a set of upstream guide vanes. If this rotor is driven into stall, the air is moving from left to right in this image. If this rotor is driven into stall, then instead of moving axially to the right, the flow starts to be centrifuged up and driven forward by the adverse pressure gradient through this slit. It then turns around and comes back into the inlet, is straightened up into an axial direction by these vanes and goes back into the fan. It's mildly astonishing that this worked at all, because you'd think that this annular slit would leak like a sieve. It would just not really do its job, but apparently it did work, and was quite popular at the time. But this upstream element isn't particularly, it's not very cost effective, and it's not good for efficiency. So in 1986, an engineer at the Flact company in Växjö, Sweden, came up with a more compact casing treatment. So it may not be apparent particularly what you're looking at here, but this is the fan blade, and there's this casing, raised casing segment. So this is the upstream casing, downstream casing, blade. There's a gap in the casing here and another gap here. And although they're not obviously curved, what you're looking at here are vanes which straighten the flow up. So we centrifuge flow into this region 4. It goes upstream and is straightened up through these vanes. And then, as it has nowhere else to go, is reintroduced into the mainstream flow and effectively follows this arrow recirculating back into the fan. Here we've got a picture me when I had hair, and of the actual veins in the casing. We can see a slit here and another one, which is where the air comes out of here. So again, this technology was industrialized and became quite routine for many years. It's still specified occasionally. It's worth having a look at how this actually works in practice, because it's really a function of how, in order to understand why this works, you really have to understand how a fan fails as a consequence of stall. So when the flow separates in the blading, you get this turbulence through the blading. Effectively, you are applying a pressure load to the fan when it's working, pressure's higher on one side than the other. When it stalls, you just suddenly release it. So you go from having a load to no load, and then it gets reapplied. And that application and release of the aerodynamic load on the blade results in a unsteady mechanical load on the blade. And the blade is like a long arm, which you're effectively getting hold of the end of and moving backwards and forwards. So where the blade attaches to the hub, there is an alternating stress, which can go and lead to a failure. So any material can withstand an ultimate load before it will break. We can superimpose an alternative load, an alternating load. So the way I like to describe it, you imagine if you had a paper clip and you wound the paper clip. So instead of being wound up like a paper clip, it was a single length, and you pulled as hard as you could, you would not break it. But if you folded it back into a paper clip and unfolded it, and folded it again and unfolded it, after 3 or 4 repetitions, it would literally fall into 2 pieces with almost no effort. Well, that's because the alternating load was creating plastic deformation in the paper clip. And so we can only withstand so much alternating load before the metal will actually break. And there is fracture mechanics, if you like, comes in later, but there at this point it's really this guy called Gerber, German engineer, came up with a relationship between steady and alternative stresses called the Gerber line, which effectively says you can pull with no alternating stress. This is the ultimate tensile strength of the fan. With no alternating stress, with no direct stress, you can have this alternating stress, and you can effectively trade the two. So the significance here is that when you're running a fan, you have mean stress due to centrifugal force, but very little alternating stress. So you can probably operate up here because you have so little alternating stress. As soon as the fan stalls, your alternating stress shoots up. So if you're operating here, you would end up in a situation where the combination of alternating and mean stress will cause a failure. So that's really why operating in stall is such a bad idea. And coming back towards the anti-stall ring, its protection is in the diminishment of the alternating stress. So there's a number of design issues for the fan designer. The Gerber line is something that has to be derived empirically. There's no theory, so you have to do a whole series of laboratory tests. It's a function of material properties and defect size. So you have to know the maximum defect size. So now the quality control in your blades and your hubs becomes important. And because of this uncertainty, designers such as myself generally divide whatever we think we can withstand by 2. So we have a design region where we've divided alternating and mean stress by at least 2 to get a design zone. If we got our Gerber line correct, this theoretical design zone should be okay, so we shouldn't see a failure, and here we're pretty sure we will. So this really brings us back to the effect of the anti-stall ring. So if we look at this, again, there is a technical paper I've got. This is all taken from a technical paper, and it can be provided after the presentation if you have a particular reason for interest in the subject. But we're going to just quickly work through this. I know we've got a lot of information on the screen, but try and hang in there for a moment. So if we start on the left here, these little diamonds, these represent the pressure volume characteristic of a fan. So from the right, pressure rises and we stall at this point. And then we have some recovery. What I did at the same time when doing this work was to measure the stress in the root of the blade. So this fluctuating stress was measured with a strain gauge. So we've got point A here, which is near free delivery, where we measure stress, and then here we've got point B, and we can see the stress relay remains quite small, then shoots up as the fan stalls. If we look at that from a factor of safety point of view, at point A, the fan is at or about a safety factor of 2 when you combine the mean stress and the alternating stress, so we're good. But as soon as we jump to point B on alternating stress, we're a safety factor of below 1. So stall, in this instance, will overpass the combined mean alternating stress capability of the material. And this is what happens. Basically, you can see this rather chunky cone at the base of the blade, and then we've got a thin aerofoil, well, what's left of it. And this line here is where the aerofoil went from being flexible to being stiff. So this part, this cone, made this section stiff enough below here that it would not move. The aerofoil above here was moving under the alternating aerodynamic loads, and this was a transition between the two. So this is where the plastic deformation, the fatigue crack, and ultimately fatigue failure came. So there's a complete predictability that this will happen. It's just a question of how long, which is the detail of the mechanical design of the fan. So if we look at the effect of the anti-stall ring, this is really both aerodynamic and mechanical. So we can look at the same curve that we were looking at previously. With an anti-stall ring fitted, the stresses were lower, the alternating stresses were lower. So let me just go back and clarify that point. So with an anti-stall ring fitted, instead of we're looking at these diamonds now, during the stable region of the curve, with and without an anti-stall ring, very similar, but instead of dropping and stalling, when the anti-stall ring is fitted, the curve continues to rise. The same strain gauge shows that we're measuring about the same stress over the stable region, and it does climb during the stall, but nothing like as much as it did. So if we go back, yes, so we can see before we were way up here. Now we are not quite as safe as we were, but we are still a safety factor of over 1. So if we did our job, we should be fine. So this gives you this is an important point in that these anti-stall rings have been oversold in the past. The people have been told by engineers and salesmen who haven't done these kind of measurements that an anti-stall ring provides complete protection, and you can quite safely run the fan install indefinitely and there will be no consequences. Well, that's not true. This assumes a defect size. This line could move down to here if you are unlucky and one particular blade had a defect that had been missed on X-ray or dye penetrant or whatever inspection that you were using. And at the risk of stating the obvious, you only need one to fail. So if you've got 12 blades in a fan, you've got a dozen fans on a job, it's 144 fans. If you missed one defect on one blade, and you end up in a situation where the fan is driven into stall semi-regularly, it will go on to fail. And then that fan is trashed. And what are you going to do about the others? Well, you're going to stop them. You're going to take the impellers out. You're going to inspect them all. Well, that's incredibly inconvenient and expensive. So my point is that just because we get this line right 99% of the time, it's not enough. We need to get it right a lot more than that. Otherwise, we just have in-service problems, which are really not acceptable. So the anti-stall ring is very good. This is a huge improvement on what we had before, but anyone who says it provides complete protection, I mean, that's just factually incorrect. It doesn't. Our safety factor diminishes. So if we just consider, for the sake of comparison, a non-stalling blade angle, that was our third option, our first option actually in my presentation. I've stripped out the stalling blade angle because this graph was getting awfully cluttered. So this is our non-stalling blade angle, and C to D was the stress. We're not generating as much pressure with a non-stalling blade angle. It's a lower blade angle, the fan's not working as hard, and we're now going from point E stress-wise to F. And if we look at what that means, oh, no, sorry, what I was going to do now is to show one problem now that I would like to touch on is that oftentimes fans are run at reduced speed, half speed maybe, when the requirement isn't so great. So what we've got here, we can see our stress is lower with a non-stalling blade angle fan. So if we just wrap up all the other things that we can do, we can run at half speed at night. What are the consequences of that? Well, we're more likely to end up in stall. So at half speed, we scale the performance right down. So this could be useful to ventilate a building at night. We can see our stresses have dropped enormously, but then the amount of fan air we're moving has dropped. If that's enough at night or on a cool day, then this might be a desirable operating regime. But the point here is we went in stall at full speed, but at half speed, the same pressure pulse or the same event has just overwhelmed the fan. So again, what I'm doing here is just wrapping up various failure modes that I've run into over the course of my career. One time did actually end up running fans at quarter speed because at night half speed was too noisy and it annoyed the neighbors. By the time you get down to quarter speed, the fan really isn't doing much at all. You've got really not much going on. But if that's enough to ventilate a building, it can be a desirable operating mode. So what I've done here is to really go through and sort of work out what the safety factors are. So at the beginning of this presentation, we had 0.3 of a safety factor in stall and 2.3 as a safety factor with a plain casing running at 100% speed. And so anything below 1, we're in danger of stalling. It's perhaps best to just go to the table now. So what we're looking at here, at full speed, we have safety factor of 2.3 when we are operating in the normal area of the curve, the stable region, And if you remember, it jumped very high. We're down to 0.3. So operating in stall, we will have failure coming. When we fit the anti-stall ring, our safety factor went up slightly in the normal region, and we were still above 1 in the stall condition. So it's not, failure isn't assured. It's not as high a safety factor as we like, but it's okay. With a plain casing and a non-stalling blade angle, similar safety factor. These are all in the same ballpark, but the best of safety factors during stall. But again, the safety factor has reduced. So a non-stalling blade angle is good, but it's not. It doesn't mean to say it's not a riskier operation. So this gives you a feel for the effect of a non-stalling blade angle versus a anti-stall casing. Clearly, for a plain casing, you just need to be very sure you're not going to operate in stall. Considering the effect of part speed, if I just jump through to the table, so 100% speed, same safety factors again, 2.3 normal, 0.3 in stall, so that's not good, it's below 1. An anti-stall casing at 50% 50% speed, we're looking at a safety factor of 10 and a 2.5 in stall. So at 50% speed, we've got a good safety factors with an anti-stall casing. Then 25% speed with a plain casing, 106 versus 7.3. So again, really no risk at all. So this is just an attempt to sort of lay out the consequences. Specifically, we want a safety factor of over 1 in stall when we're at less than 100% speed. So again, apologies for the speed I'm going through this. We just only have so much time today. There is supplementary material if this is directly relevant to something you're doing and if I've blown through it a little bit too quickly. So some practical examples and cost implications. These different strategies that I've outlined, a fan that can generate a high pressure, so won't go into stall, an anti-stall casing to protect the fan in the event of stall, and a non-stalling blade angle. They have implications for both the capital cost and the operating cost of the fan. So my assumptions here may not be relevant to any future project. This is a typical duty point for a central tunnel ventilation fan. Typically, they have to have a high temperature requirement. They are typically also used to ventilate the subway in the event of just normal operation during the day, so typically 12 hours a day. And I've picked a cost of electricity and a cost of capital here and a period of assessment of 10 years. I'm not saying that this would be your cost of electricity or cost of capital or 10 years, but they're not unreasonable. And so it provides a basis for making an assessment of the relative merits of these different selection strategies. So if we look at non-stalling blade angle, anything below about 18 degrees is non-stalling. Here we've selected at 15 degrees. Typically, the curve isn't published back to zero flow because it's bad practice to select in that region. So this would be a typical non-stalling selection where you're selecting kind of at the edge of the allowable selectable range. And note here we've got a 2.5 meter 6-pole fan. Here we've got a 1.8 meter 4-pole fan It's going faster, and that is why this is generating considerably more pressure. But at around 24, 5, 6, around 27 degrees, this fan most definitely will stall and stall badly, and if operated in stall, will fail quickly. So we've got a good margin here, and 1.8 meter fans are cheaper to build than 2.5 meter fans, and 4-pole motors for the same power are less expensive than 6-pole fans. So the motor for this fan and the impeller and casing for this fan are considerably cheaper than for the larger, slower, non-stalling blade angle. With an anti-stall ring, we've deliberately selected in the stalling range. Technically, we haven't selected in the stalling range. We've selected in the stable operating range with a reasonable margin, however, knowing that a pressure pulse will drive us into stall. So it's a valid selection. We simply know that the circumstances in the application will drive us into the stall region. So this is a stalling blade angle. The pressure pulse will take us into the stall region, and we are assuming that the anti-stall ring will prevent the fan suffering a mechanical failure. This one is in between the two. It's a 2.24 meter diameter casing with a 6-pole motor. It's almost as expensive as a 2.5 meter, and probably a very similar price because these anti-stall casings aren't cheap. So the 6-pole motor will be the same price. That 2.24 meter casing plus the cost of the anti-stall ring is probably getting you to the cost of a 2.5 meter with plain casing. So if we look at a through life cost, they're all selected with slightly different duty point efficiencies. They've all got a different capital cost because they cost a different amount. They'll use a different amount of electricity per year because they've got different efficiencies, and so we will end up with a different cost of ownership over 10 years. So it's probably best to just go to the table. So what we see, total cost, the 1.8 meter fan, the 2.5 meter fan is not the most expensive. Yes, the anti-stall casing is really quite expensive, but it's more expensive than 1.8, but it is the cheapest to own. So we can see that the one that each of these capital costs, each of the absorbed electricities, and therefore the cost of electricity per year gives us these running costs as a potential of total estimated costs. So I think perhaps the most direct measurement is to look at the total cost of ownership over 10 years. And these are different. But if you think about it, this 1.8 meter fan, it's the most expensive to own over 10 years. It's the cheapest to buy. What isn't included in here is the fact that the 1.8 meter fan, if it's going underground, it's going to need a bigger plant room than either of these other two. So that the cost of digging a bigger plant room underground could overwhelm these costs quite easily. So conclusions, we got 3 selection strategies to help avoid stall. There isn't a correct approach. The anti-stall ring is popular in some areas. It does reduce the impact of stall, but it doesn't give you complete protection. Alternating stress levels of a tested fan did increase significantly when driven into stall, but it still provided a good level of protection. So they do work, but they're not perfect. The mechanical design has to account for the effect of stall. So it's important. If you've got any concerns about the fan company you're buying fans for, just start asking them a few questions about the mechanical impact of alternating stress and their approach to fatigue, failure, and fracture analysis. You'll soon find out if they know what they're talking about. Good quality control, X-ray inspection and such like is important. So asking for records of that in any specification is helpful, can help reduce your risk. This paper is available free of charge from this website and covers the real technical content of this presentation, and you're more than welcome to download that at your leisure. And AMCA have some other resources available to you should you wish to avail yourself of them. Oh, I think that's it. I think I'm done, Lisa.
Okay. Thank you, Jeff, very much. That was fantastic information as usual. We are going to now get to our Q&A segment. So if anyone does have questions for Jeff, please go ahead and enter those into the Q&A panel, and we will get started on that. And I have a few here. Let's see if the camera will work today.
Do I have to stop sharing?
No, you are okay. Thank you very much for asking,
Okay.
So while I'm waiting to see if my camera feels like cooperating today, I will remind everyone that the PDH credits recording or the PDF version of today's program that will be made available on the Odell website within 48 hours.
I think we got a problem with your audio, Lisa. You're cutting in and out.
Oh, I'm sorry. Can you hear me?
Oh, yeah, can hear you now.
I will not tempt fate and keep my camera right where it likes to be, which apparently is off. So, four questions, Jeff. One question that we have here is when a fan stalls, why do fan blades fail mechanically?
Well, it's a good question. If you think about what a fan is actually doing when it's operating, the fan blades are rotating, and you've got a pressure field over one side of the blade and a different pressure field over the other side of the blade.
Mhm.
So the actual it's that pressure difference which is driving the air to a higher pressure on the fan outlet. So under normal operation, you've got a high pressure on one side of the blade and a lower pressure on the other, and the motor is effectively driving the impeller around against that. When a fan stalls, the flow no longer goes through the blades, it kind of stops and gets centrifuged up the blade and comes out of the front. That pressure difference across the blade is released, and so you go from having a pressure load on the blade to not. And one of the peculiarities of axial fans is a phenomena called rotating stall. Excuse me. Only one blade to blade passage breaks down, and As that passage breaks down, it results in the blades on either side suffering a release of pressure load. But then that stall cell jumps to the next blade passage, and that stall cell typically rotates at about 50% rotating speed. So as the stall cell jumps from blade to blade as the stall is developing, the pressure is applied and released, and applied and released. As the pressure is applied, the blade is bent. As it's released, it springs back. There's no pressure load on it. And then the pressure load is reapplied. So it's the equivalent of getting hold of the end of a blade and pulling it backwards and forwards, which is the equivalent of unbending, a paper clip and then rebending it and unbending and rebending. And there comes a point where it literally falls apart. So it's really the aerodynamic breakdown and then re-establishment of the aerodynamic flow field that results in the sudden release and reapplication of the pressure load. And that's what induces the stress in the blade at the point where it goes from being mobile and can move to the point at which it becomes stiff, where it is approaching the hub.
Mm-hmm. All right. Thank you for explaining that. Um, Another question that we have is you had talked about anti-stall rings reducing the mechanical impact of a fan diving into stall. Is there anything that can eliminate the impact, however?
Um, that's a good question. There are some applications, and I'm thinking particularly of the axial fans that go into submarines and warships, where the requirement is that the ventilation system must continue operating even under the most dramatic of circumstances.
Mhm.
In those situations, the fan is so over designed mechanically that you can operate it against a closed damper indefinitely and it will never actually fail mechanically.
Hmm.
And that's to account for the fact that, if it's all going terribly wrong, and the last thing you want is to then have the ventilation system shut down and suffocate to death. Presumably people are
Mhm.
shooting things at you, and adjusting the ventilation system is not really a priority. But you still have consequences. You still are driving the fan into the stall. It's just that it's so over designed mechanically that the consequences are manageable. The
Mhm.
nearest thing to the elimination of consequences that I personally have been involved with was the design of a fan with a very flat pressure volume characteristic, where effectively, if you think about the characteristic of the rotating blades, static blades also have their own characteristic. So the downstream vanes from a fan have a characteristic. So if you design the rotating blades to peak at one flow and the static vanes to peak at a different flow, you can flatten the characteristic of the fan. It's not a very efficient fan, but it's got a very flat characteristic, which is good in some applications. And I noticed that a unintended consequence of that design process was a fan that effectively didn't stall,
Mhm.
even though it was operating in a pressure flow region that normally would. if the guide vanes downstream had been designed to match the rotating blading. In today's energy conscious world, the probability of anybody wanting to do that is pretty minimal.
Mhm.
It was difficult. There was months of CFD to get it working, and the end result was really not a very efficient fan, but worked in the application. So that was one of those oddball niche applications
Mhm.
that had very particular demands. The ability to have a non-stalling characteristic with, for all practical purposes, no consequences of stall was an entirely unintended byproduct of the process. And I do remember at the time, oh, fancy that. If this wasn't so hard, that would be really useful. And then I never did it again. So there we are.
Well, probably, as you said, not the most common of situations. So another question that we have is, when you are assessing a fan's mechanical design, what would be an acceptable mechanical safety factor?
Well, that's a good question. I always use 2, but if we say the answer's 2, well, 2 what? And that's a little bit more difficult to answer. So what I mean by 2 is 50% of the maximum direct and alternating stress that the empirically derived Gerber line says I can stand for the maximum defect size that I allow through use of a quality system that includes X-ray inspection, mag particle inspection, dye penetrant inspection, or whatever other form of inspection is appropriate. So just say the answer is 2. I want 2 of them. It's not enough. As soon as you get into an answer that is enough, you're now really drilling down into what the fan company is doing, and that actually in practice you can't get an answer to that question. You just can't in practice. If you really want, if you're in a situation where you're going to drop these fans in and then build a concrete box over them and put 100,000 tons of dirt on top, it's really very inconvenient. We've now got a 2.5 meter fan inside a plant room with a 1 meter door or 1 by 2 meter door. I mean, it's not going to go well if somebody says, do you mind taking that out? Well, actually, we do mind. So if you're in a situation where it's just so massively inconvenient that you have to know what the safety factor is and do so with confidence, you end up paying me or someone like me to go and do a supplier audit. And I can tell you, when I show up, I'm about as welcome as a pandemic, because I ask the questions that they don't want asking. I drill down into their laboratory test methods. I drill down into their engineering methods, and I'm generally very rude about what they're doing and insist that they do better, if only for this one contract, should they wish to be paid. So there isn't really much of a middle ground. You can say in your spec, and must be designed with a safety factor of 2. Did you design for a safety factor of 2? Oh, yes, we did. You promise? Yes. You're not lying? No. They're lying. What can you do? It's very difficult. Well, there isn't, as I say, there isn't a middle ground. You either put it in the spec and then when it fails, just hand it over to the legal department. Then you might see me showing up anyway. Given my expert
That's a
witness.
different webinar.
That's a different webinar. But yeah, if you're really if you're really concerned, your first step might be to send your quality manager to go and poke around and see what happens. The trouble is, the quality manager is probably not going to be able to ferret out the necessary details in the engineering department, and they'll tell you it's a trade secret, they'll tell you that it's confidential, and you really need somebody who's been rude to people a lot to get past all that. That would be me. So yes, I mean, I'm sorry I can't give you a better answer, but yeah, again, it's like I think the practical thing is to, I don't know if you've ever been into a foreign country where they've asked you to fill in this customs and immigration thing. Have you ever been part of a terrorist organization? Are you a member of the Nazi Party? Did you involve anything during, I wasn't born until 30 years later. How could I possibly have done any of these things? They're not asking you because they think that you're going to tell the truth. They're asking you so that you have lied in writing, and now we can take legal action against you. So putting a safety, I mean, just asking for a safety factor of 2 in the spec's not enough, but there are a series of questions that you can ask in the spec. Confirm in writing you do A, B, C, D, E, F, and G. Then it fails in service. You didn't ask them because you really expected them to not say yes. You asked all those questions because your legal department say if they say they do all these things, then when we go to court we will win. But again, that's a different webinar. So again, yes, putting people in a situation where they're asked these questions is reasonable, but it's a reasonable commercial thing to do. Technically, what are they going to say? Sorry to sound cynical. I've just been doing this for too long.
No, I appreciate that perspective. And I'm actually, before we wrap up here for the audience, I'm going to do 2 shameless plugs, but they are for the benefit of education at large. There really is a webinar that AMCA did on July 28th of this year. If anyone is interested in going to the AMCA website to view it for free, of course, Jeff Sheard and another gentleman did a webinar about how to talk yourself into and out of legal trouble with a focus on the air movement and air control industry. So for anyone who does have an interest in that, please feel free to go to the AMCA website and look up that webinar. Again, it was from July 28th of this year. The other shameless plug that I'm going to put out there is for anyone planning on attending the AHR Expo in Las Vegas at the end of January. Jeff is one of our presenters. AMCA is having 8 educational programs for free at AHR Expo. If you go to the Expo website, you can look all this up under education. And Jeff's presentation on January 31st will, I think, be a huge draw. And the topic is living with a skill gap, designing higher efficiency fans with a less experienced workforce. And I think all of us are familiar with the topic that not only how do we do more with less, but with current generations of experts in the industry retiring, what happens when the younger generation comes up behind them to take their place and they do or do not know what needs to be known about the industry, the equipment, the policies and procedures, etc. So please join us at AHR Expo. So those are my 2 shameless plugs, and you all will see some upcoming promotions about the expo and the AMCA free education programs that we're hosting there. So as always, we're thrilled to have Jeff joining us there, and we're thrilled that he was able to join us to wrap up this education series. And hopefully everyone who has participated, not just today, but in general, has benefited from this program that we have conducted with Odell Associates. So Jeff, thank you again, as always, for your outstanding presentation and your time and expertise.
No, Always a pleasure.
Well, thank you so much. Everybody, happy holidays. Be safe and enjoy, and we will see you all very soon. Take care.